Okay, we're going to start with number 25. And you're going to use that chart on the back page of your notes, the first set of notes we gave you. And so what I know is I have this situation here. I would have preferred this 2 to be written down here, but it's the same thing with the C. I got a 3 for the CL. So that's what I like for mine to look like. So all I'm interested in is what's going on this side. So I look at the sulfate group, and I say, well, the sulfate group is paired up with the aluminum, and when it pairs up with the aluminum, it's insoluble. So I'm going to put the word AQ here. I'm sorry, let me say that again. When the sulfate group is paired up with the aluminum group, it is soluble, so that just doesn't make any solids, it just keeps it aqueous. I look at the silver and the chlorine. If you look at your notes, when chlorine reacts with silver, it makes a solid, so I need to put a little S right there for solid. Sodium and bromine, look at that one. Sodium bromide, does sodium bromide give me anything? Well, when I look at sodium bromide on the activity chart, if it's paired up with the Br minus, it's paired up with sodium. Sodium 1 is a alkali metal cation, so it does not give me anything. It is aqueous. There is no solid made there. Then I look at my sulfur. My sulfur is paired up with cadmium. It will give me a solid. I look at the nitrate. Nitrates never give you a precipitate, so that one's aqueous. I look at my iodine. If my iodine is paired up with calcium, it doesn't do anything either. No solid precipitate is produced, so there is no reaction for that one there. Number 28, nitrates again, they don't do anything. They never give you a product. They just stay soluble. Hydroxide, if it's paired up with iron 3, will give you a solid. Going down to this one, nitrates again, never give you anything. They stay aqueous. Sodium chloride, chlorine when it's compared with Na, which is an alkali metal, does nothing. Gives me no precipitate, so there is no reaction there. And if it's no reaction, you don't really even need to put those aqueous there. If it's no reaction, you just put NR, life is good. Okay, we're going to move on down. Okay, notice that this graphic comes directly out of your notes, and it says describe each type of radiation, including name, symbol, energy, and ability to penetrate different substances. So I said for the alpha particle, and I said a lot, because I want to make sure I covered everything. So I said, well, for alpha decay, the symbol is the Greek letter alpha. And what happens is a helium nuclei, or nucleus, I guess I should say. A helium nucleus is emitted from a radioactive source. All right. The helium nuclei, which looks like this, contains 2 protons and 2 neutrons. So that means the charge is 2 plus or plus 2, and that comes from the 2 protons. It's not high energy. It can be stopped by a sheet of notebook paper. So not high energy. By a sheet of notebook paper. Notebook paper. So that was pretty straightforward. All right, let's erase that and go on to the next one. The next one is beta. All right, so I said on beta, that beta emission, and that's the Greek letter for beta, has that little tail. Is the emission of fast-moving electrons, so it's high energy. Okay, those fast-moving electrons, we give it the symbol to show that it's 0, -1, or some people write it as 0, -1, beta. And that just tells me the charge is a -1 because it's an electron and it has basically no mass. Because when you look at the mass of an electron compared to that of a proton or a neutron, it pretty much has no mass, okay? So the charge is -1. And it penetrates more than your alpha, but not as much as your gamma. It can be blocked by aluminum foil. Or a thin piece of wood. T-H-I-N is what that's supposed to say. Piece of wood. All right, so that's beta emission. I'm going to erase that and talk about the gamma. All right, gamma. Gamma is electromagnetic radiation. E-C-T-R-O, electromagnetic radiation. High energy photons, so that's the highest of energy of the three that we talked about. Are emitted. There is no mass, and there is no charge. The symbol looks like that right there, something close to that. Extremely penetrating. Can be partially stopped or somewhat stopped. By several feet of concrete. Or several inches of lead. So I think that takes care of gamma. All right, now it says in the figure to the right what type of nuclear activity is represented. So this is uranium-235. It splits into bromine and lanthanum in this particular one. And then I have two more neutrons. These are neutrons, and this is a neutron there. So when I have that split, that is referred to as nuclear fission, because that's what fission means, is to divide. Which particle will complete this reaction? So I said, well, 59 and 60, I know I need a 1 here. 27, I need a 0 there. So 1, 0, that's going to be a neutron. Okay? So that has no charge, but it has a mass. All right, let's scoot on down. Okay. This one says, for questions 33 through 37, determine what is oxidized and what is reduced. Identify the oxidizing agent and the reducing agent. So I looked at strontium. Strontium by itself has no charge. Oxygen by itself has no charge. But when I brought them together, that was a +2 and a -2. How do I know? I looked at the periodic table. So strontium went from 0 to +2, so it lost some electrons. Oxygen went from 0 to -2, so it gained some electrons. Remember, oil rig. Oxidation is loss of electrons, so strontium lost electrons, so strontium was oxidized and served as the reducing agent because it caused oxygen to be reduced. And oxygen served as the oxidizing agent because it caused strontium to be oxidized. Lithium, 0, 0, plus 1, and then -2 right here is what I should have said. So lithium went from 0 to +1, so it lost an electron. And remember, oxidation is the loss of electrons, so lithium was oxidized. Sulfur went from 0 to -2, so it gained electrons. So reduction is gain of electrons. If something gets reduced, it serves as the oxidizing agent. If something gets oxidized, it serves as the reducing agent. Cesium bromide. Cesium was a +1. Bromine is a -1. Cesium by itself is 0. Any element by itself has no charge at 0, and that's 0. So cesium went from a +1 to 0, so it must have gained an electron. Bromine went from a -1 to 0, so it must have given up an electron. Oxidation is lost, so bromine must have lost, so it got oxidized. If bromine got oxidized, cesium had to have been reduced. Cesium was the agent that, or cesium caused bromine to be oxidized, so cesium is called the oxidizing agent. And then bromine caused cesium to be reduced, so bromine is the reducing agent. Oops, I almost skipped number 36, sorry. Let's get this stopped and we'll talk about half-life.